Analysis Tutor. Here we're going to talk about the current divider circuit. The last section we talked about voltage divider. It was when we had a source voltage that we wanted to split up so that we could use a portion of the voltage in our, in our load, for instance. This section is going to be the same concept, except instead of a voltage source, we're going to have a current source, with the arrow, and then we want to split that current into different values. Like maybe we require 3 amps in our circuit, maybe we only have a 10 amp current source. So we need to find what equations required to split that up so that we know what we're looking at here. So that's the basic idea. Now if we wanted to draw graphically what this means, it basically means that we have a current source, we'll call it I sub S. This is what a current divider would look like. Instead of 2 resistors in series, a current divider is going to be 2 resistors in parallel, or at least one way to make a current divider. Right? Now let's make sure we understand this. Let's call this resistor R1. We'll call this resistor R2. And just to make it clear, the current flowing in this leg we'll call I sub 1, and the current flowing in this leg we'll call I sub 2. So you know from experience that the current is going to flow up, it's going to hit this node, part of it's going to go here, part of it's going to go here. This is the current division. The junction points, the nodes, that's where the current's splitting. So when you do a current divider circuit, what you're doing is trying to take your source current, whatever it is, and trying to split it up so that you can get 2 amps or whatever it is you need to go into your particular load. I could just give you the current divider equation to show you how to calculate these legs, but really it's instructive to derive it a little bit, so you kind of know where it comes from, right? What we really know here, let me use a different color here. What we really know here is that there is a voltage here, we'll call it V. And this voltage is the same across this resistor and the current source, right? Because they're all in parallel like that. So what we can do is we can recall, we know that V is equal to IR, so we can say that this voltage right here is equal to I1 times R1. Wouldn't you agree that's the case? Because you have I times R, that's the voltage here. But it's also equal to I2 times R2 because that's the current and the resistance over here. And they're all connected in parallel, so the voltage is the same. But also note that these guys are in parallel. We already learned how to combine 2 resistors that are in parallel. So if we were to do that and make an equivalent resistance here, the voltage across that equivalent resistance would be the same V as what we have here. So it would be, if we did it that way, it would be I source times the equivalent resistance of these 2 resistors. In other words, if we combined resistances here, we have a single resistor fed by I sub S. The voltage across it would be I sub S times the equivalent resistance, IR, right? But we know what the equivalent resistance is. It's simply the following. It's product over sum. R1, R2 divided by R1 plus R2, right? So we know that. So what we've really drawn here is a very massive thing, but really what it says is the voltage across this is the same as the voltage across here, same as the voltage across here, same as the voltage across if I made an equivalent resistance, which I know how to do. That's all this is saying. So everything is equal to each other. So what I can really say then, let me change colors here, is that if I want to take this guy and set it equal to this over here, then I could say I1 is equal to R2 over R1 plus R2. And I missed one little thing. I1 is equal to IS times this. Make sure you understand. What I'm saying is I'm setting this equal to this. The R1 cancels with the R1 up here, disappears. The rest is the same. I1 comes from here, the source current comes from here, and you have this guy right here. Let me do the next one and then we'll talk about it. I can set this also equal to this. And when I do it, I'll get I sub 2 is equal to I sub S R1 over R1 plus R2. All right? These are the current divider equation. These are the current divider equations. What it is basically saying, because what I did here is I set it equal, I canceled R2 out, and then the rest just stays the same. What it's basically saying here is that if you have a known source current feeding 2 resistors like this, if you want to calculate the current in the first leg, you just take that current that you know, and you multiply it again by some factor. Doesn't this look quite a bit like the last section? It looks a little bit like the last section. It's a little bit different though, because if I want the current in leg 1, I have to take the resistance in leg 2 on the top divided by their sum. If I want the current in leg 2, I got to take the resistance in leg 1 and divide by their sum. But what I'm really doing though is I am creating a factor, something less than 1, that I'm going to be multiplying by my source current that's going to give me proportionally, what's going on in each leg. Much like the voltage divider, looks very similar. You take the source voltage, you multiply by some proportionality number that's less than 1, and you get the voltages that must sum up to be equal to the source voltage. Here, I'm calculating using a different proportionality multiplied by the source current, giving me the current in leg 1, current in leg 2. Of course, they have to add together to give me the source current. The only thing you really have to remember here is that if you want it in leg 1, you got to use leg 2 on top. If you want it in leg 2, you have to use it in leg 1 on top for the resistances. So you have to use the opposite leg, and that's really the main thing here. All right, now this is the problem we're going to work here, and really what we want to do is find out what the value of this voltage is across that 90 ohm resistor there. So again, we have a current source, 2.4 amps. We have resistors known everywhere. We can use Kirchhoff's laws if we wanted to solve this, but then we start looking at it and realizing that, hey, this current splits and goes this way, and it also splits and goes this way. And we know how to do series parallel reduction, so we can simplify this circuit into something that looks like a traditional current divider. Then we can use the current divider equations to find the current going this way, and then we can find that voltage. So we're going to apply what we know now to solve this problem. So the first thing we do is we take the obvious. This guy right here, 15 plus 20. This is going to be 35 ohms, right? So that's the obvious guy. But then the other guy we want to look at is we start looking around and we say, well, these guys are in parallel, so we can kind of tidy this up a little bit. And we say equivalent. This is two guys, so we can do product over sum. So it's going to be R1, R2 divided by R1 plus R2. The product is 10 times 90. The sum is 10 plus 90. All right? And so what we're going to get here, when we have this, we'll have 900, and then we'll have 100. And so what we'll get is 9 ohms. So I have 9 ohms for this part. Now let's go and redraw the circuit here, because I think at this point we've simplified so much stuff that it'll be worth it to do that. So here we have 2.4 amps. Okay, on this side we're saying that we have 35 ohms. And on this side we still have our 6 ohms. We haven't done anything with that, but we replaced all of this stuff with 9 ohms. And we're also saying, notice, that since the voltage V0 is across the 90 ohm resistor, but since we replace this with a single resistor, the voltage drop V0 is now over 9 ohms because we've combined these into one guy. V0 is across 90, it's across 10, and it's also across if we replace it with another resistor. So now we've kind of simplified the circuit to saying, okay, here's a new circuit, it's much simpler. Now we want to find out what V0 is across this equivalent 9 ohm resistor. All right, now again, there's many other ways you could do this. You could do Kirchhoff's laws, you could do other stuff, but you recognize it immediately as a current divider. So that's going to make things easier. So let's label some things here so we know what we're talking about. Let's say going this way, we're going to call it I sub 1. Going this way, we'll call it I sub 2, so we can have some labeling. All right, so first, let's find I sub 1 just for kicks. What did we say it was going to be equal to? We said let's go back to our current divider. It's going to be the source current times the opposite leg over the sum. Source current times opposite leg, R2, over R1 plus R2. Source current's 2.4 amps. All right, and since we're finding this current here, we go to the opposite leg and we say 35 ohms is the guy in the opposite leg, and then we have to add up everything because it's R1 plus R2. When you go back to our original drawing, it's whatever's in the other leg divided by the sum of the resistances in the different branches. So what we really have going on here is on the bottom we'll have the 35 ohms here plus the resistance in the other guy, and I'm just going to leave it like this. 9 plus 16, we're going to leave it as 15. I should say 9 plus 6 is 15. So what we have is source current times the resistance in the other branch divided by the sum of the other resistances in all the branches. And what we have then is I1 is equal to 1.68 amps. That's what I1 is equal to. That's really all we need to get the answer, but just for giggles and to get some practice, let's calculate I sub 2. It's going to be the source current, 2.4, times the resistance of the other leg. Here we have 9 and 6. We know that's 15, so we'll have to put 15 there, divided by the sum. So we'll have 15 plus 35, right? And so when we do that, we're going to get 0.72 amps for this guy. And if you notice, 1.68 plus 0.72 sums up to 2.4 exactly, which it has to, right? So now that we know these currents, if what we're asked to do in the problem is find V naught, then what we need to do is just, knowing the value of I sub 1, calculate that. So we know V is equal to IR, right? And the current we calculated is 1.68. The resistance is 9 ohms. Remember, it's an equivalent resistance. But 1.68 times 9 ohms is going to give us, the voltage is 15.12 volts. And that is the voltage across, in this case, it's across the 9 ohm resistor, which is the same as what we're trying to find in the original problem. So let's go back from the top, because it's not so obvious at first. We first simplify this into an equivalent resistance. We simplify this into an equivalent resistance. But when we redraw our picture, we recognize that the voltage drop across these resistors is the same voltage as what would be across the equivalent resistance. That's what an equivalent resistor is. You take what you have out, you stick a single resistor in, the voltage, everything else should be equivalent because that resistor should represent the original network. Okay? So here, I could add these together, but I don't want to leave it split up because I want to leave V naught in here for you to see it. So to find I1, we take the source current times the opposite leg on top divided by the sum of the other legs on the bottom, right? And then that gives us our number here. And then for this guy, it's just to get practice, it's 2.4 times the opposite leg. The opposite leg is over here, so we use the total resistance here divided by the sum right here, and then we get the number. Now these guys must sum up to what we have. Once we know the current, we know the current's going through this 9 ohm resistor, bam, it's IR, voltage is equal to IR, and then you get the answer. And that's basically it. So, current dividers, they're used some, but since current sources are not really something you typically buy off the shelf and use, there is a use for a current source, don't get me wrong, but usually things are powered by batteries or voltage sources or things like that. You won't see current dividers that much, but there's lots of scenarios where within a circuit, you may not see a current source running around a circuit so much, but there's a lot of examples when you have transistors or something going on where you have current coming in and you'd like to split it into certain number of legs or whatever so that you can feed a certain amount of current off to one side and to do something with it, and then in the other branch you might feed a certain amount of current off to do something else with it. Maybe your electronics you've got hooked up to those different branches are require only that much current. Maybe you don't want to put too much current in it because you might blow it up or you might burn it or something like that. So use a current divider for that. If you have a known current value coming in, you want to split it up. If you have a known voltage and you want to just get a voltage going into the output, which is more typical, then you would use the voltage divider. So going back to the equation, to find the current in the different legs, it's just the source current, and then you go to the opposite leg. So in this case, R2 divided by the sum of the resistors. Same thing, when you're finding R2, you go to the opposite leg on top divided by the sum of the resistors. So you need to spend a few minutes getting comfortable with current divider equation, voltage divider equation. Make sure you understand that. And then also don't confuse it with how to do series parallel, because when you do parallel combination of two resistors, it's product over sum. R1, R2 divided by R1 plus R2, and that can get a little confusing too, this equation here, because it has a lot of resistance divided by R1 plus R2. They all have R1 plus R2 in the bottom, so you need to make sure you're comfortable with this equation and what it means, and the voltage divider equation, what it means, and the current divider equation and what it means. Now in this course, this volume 1 of electric circuits, I've really tried to give you the core tools to understand anything about circuits. The number one thing you need to understand is what is voltage, what is current, what is resistance, and how are they different. Don't mix mingle those terms, understand what they are and internalize it, and get an idea for what what the voltage is and what the current is and how they relate to one another, right? Secondarily, we go through and we have a survey of circuit components to kind of give you a little primer and a little motivation. But the reality of it is that all the circuit techniques that we learn, we always learn to apply to resistor networks first because it's easier and because all of these techniques we're learning now, you'll find out later, they also apply when we're talking about AC circuits and with capacitors and inductors. There are some differences, but the basic idea is basically going to stay the same. So we focus on resistors for a while. We've learned about Kirchhoff's laws, we've learned about Kirchhoff's current law and voltage law, we've learned about power, and probably honestly if I had to pick one thing that was one of the most important things that I've taught in this lesson, in this course, that I've tried to get across, is the sign conventions. The sign conventions can fail you faster than anything, because if you don't understand the sign conventions, you'll never be able to write a power equation correctly. You'll never be able to write a Kirchhoff current law equation correctly, and you'll never be able to write a voltage law equation correctly. And if you can't write those, you can't solve anything, right? And also you'll find out in the next volume when we do some other analysis methods like node voltage methods and mesh current methods, you'll find out that those sign conventions are integral into that as well. So that's probably one of the most important things. If you don't get it, you won't go far. So make sure what you get out of this course is good understanding of what current voltage resistance is, these sign conventions, and also good practice with Kirchhoff laws and just getting a good foundation in how power works and power absorbed and power delivered. Follow me on to the next volume where we'll talk about more advanced circuit analysis techniques for more complicated circuits, and we'll go on from there, eventually getting into alternating current, resistors, capacitors, and other circuit elements that we add into the mix. Those things are mostly used in AC circuits. That's why we study them a little bit later. I'm Jason with MathTutorDVD.com. I hope you've enjoyed this course. Work your problems, work all of these problems. When you're done with this, go to your book, work 20 or 30 or 40 more problems. With practice comes confidence. With confidence, will help you get very, very good grades and good understanding of circuit analysis.